So let's first talk about some sign conventions. Okay, so and remember this is in SI units. Okay, so we have these three circuit elements that we can use for our basic AC circuits. They're all linear circuits, but in order to do circuit theory properly, we do need to understand, where all the pluses and the minuses go. So, oops, for resistors, we know if we have, some kind of a thing, an Ohm's law. So there's a current. That means that the voltage drop occurs in the direction of the current. So the potential on the left-hand side is higher than a potential on the right-hand side. So when we write Ohm's law, we assume that the potential drops in the direction of the current. Okay, so that means that when you do your Kirchhoff loop rule, you need to pay attention to the sign. Sign is important. Okay, now capacitors. So when we do capacitors, we draw this thing. Let's say this thing is positively charged, V, and this is negatively charged. That means that there's an electric field in between. And the potential always drops in the direction of the electric field, and of course the potential is split in two. That means the left hand is at plus Q, and the right hand is at minus Q. And pay attention to your factors of 2 here. So when we write C is Q over V, we are assuming such a distribution, a plus V over 2 on one side, a minus V over 2 on the other side. So the potential difference is V, but the charge difference is actually 2Q. Okay? This is a neutral object. It doesn't need to be neutral, but that's just how we use capacitors most of the time. So we start with a thing that is neutral, and then when we charge it, we displace some charge and we take it away from the right side and we put it on the left-hand side. So the net charge still remains 0, but there's a charge difference of 2Q between the left and the right-hand side. Okay, so V goes down in the direction of, left to right. So if we follow this, from left to right, the potential on the left-hand side is higher than the potential on the right-hand side. Now, when we use this in an AC circuit, we use the relation that, let's do this in black. We use the relation that I is Q dot. Okay, what does that mean? Well, if Q dot is positive, that means that we're charging the capacitor. That means that the current goes in this direction. Okay, so the current flows into the capacitor and then out of the capacitor on the other side. That means that the positive charges are coming onto that left plate, and that charge is increasing. And then the charges are being removed on the right-hand side, so that charge is decreasing, it's negative, and it's going to become increasingly negative. So when we connect this thing in a circuit, we have, if we follow this in the direction of the current, we have a voltage drop. And that voltage drop, so there's a voltage drop in the direction of the current, given by QC. And of course, that means that when we traverse our circuit, we need to pay attention to which way the current is going. Okay. For inductors, we have something similar. So let's say we have some kind of a solenoid. And let's say we have a current that goes in this direction. Now we know that the EMF is L di dt. If I is increasing as a function of time, then the E is going to be in such a way that it tries to oppose what we're trying to do to it. Okay, because this is actually Lenz's law. So if I is increasing, so let's say di dt is positive, that means that we're trying to increase it, and Lenz's law is trying to oppose that. Then the left-hand side would be positive and the right-hand side would be negative, because you need to overcome that potential because it's trying to oppose what you're trying to do to it. So that means that also, in this case, if di dt is positive, that E goes down in the direction of that current, and it's going to be L di dt. Okay, so potential drops, oops, in the direction of the current. And that fixes the sign. So we know that it drops in the direction of the current if di dt is positive. If di dt happens to be negative, then we can trust our algebra, make sure that that sign is going to be reversed, and the whole thing will be fine. Okay, so it would drop by an amount of L del Ti di dt. Doesn't need a partial. Okay. So when we do our circuit analysis, we have some kind of a source. We have a resistor, capacitor, and an inductor. And let's say we start off with a current in this direction for some part of a phase, an R, a C, and an L. We can just write the potential that is applied here. That's your V from the source. Oops, V from the source is equal to all the drops, IR plus Q over C plus L di dt. Okay, and then when we convert this to phasor form, we just say the voltage phasor from the source is IR, but now this is the current phasor, and then plus, and this is the current phasor times the impedance of a capacitor, which is 1 over I omega C, and then plus current phasor times I omega L. Okay, so you see how those sign conventions that we picked in the beginning follow straight through even when we do the phasor notation. Summarizing. We have for a resistor, we have the impedance Z sub R is just R for capacitor. C sub C is 1 over I omega C. And for an inductor, I omega L. Okay. Now let's talk about filters a little bit. So filters. We have done a couple of basic filters already. These are just filters that are organized like a simple voltage divider. So we have some kind of an impedance here. And then we have some kind of an impedance here. Let's call this Z1, let's call this Z2. And we assume that we have some kind of an ideal load here. So let's say multimeter with input impedance much larger than all the other ones in the circuit. And we have some kind of a source here. And the source is just driving some kind of a current through the circuit. And because the input impedance is high, all the current that goes through the first one goes through the second one. So that's what makes it an ideal voltage divider. And this is the most simple circuit to deal with. And we usually ask ourselves, you know, what is the output voltage over the input voltage phasor? And we call that thing the transfer function. And the transfer function captures the entire behavior. And it's always going to be, the output voltage is always going to be some kind of a current phasor times whatever is on the output, which is Z2, divided by the current phasor, the sum of these two. And this is always going to be something like 1 plus Z1 over Z2 minus 1. And you can very easily set up any kind of an AC circuit and analyze it. And the analysis always proceeds like this. So for instance, let's say we have a Z1 is, let's see. So Z1 is R, Z2 is 1 over I omega C. Okay. Now, you see that we have a Z1 over Z2. So that thing in that denominator becomes 1 plus I omega RC. Now, in the limit of omega going to 0, that thing is 0. And that means you add it to 1, and the transfer function is 1. Okay, so H is 1. And the limit where it goes to infinity, it's 0. So this is what we mean by a low pass filter. Low pass filter. Okay, so we could even make a little table. So, you know, a Z1, a Z2. So let's say we have, you know, an R and a C. I'm not writing the actual expression here. We could do it with a C and an R. And then the limit where omega goes to 0 or omega goes to infinity, we can write those down. This is where it's 1 in the low frequency limit and 0 in the high frequency limit. So this is a This is a low pass filter. And when we swap these two, the Z1 and the Z2 are swapped. So that means instead of Z1 over Z2, we get Z2 over Z1, if you want to think about it that way, which means that these two limits, they swap, because instead of having omega, you get a 1 over omega. So the C and the R swap places, just means that we go from a low pass filter to a high pass filter. Okay. Let's say we do RL. Now, usually when you swap a capacitor for an inductor, instead of having a 1 over omega, you get an omega in the impedance, which means that instead of having a low frequency limit of 1, you get a low frequency limit of 0, because instead of using something that goes like 1 over omega, you use something like omega. Okay, so this becomes a high pass filter. And then, of course, if we swap these, oops. This is a low pass filter. Okay. And then, of course, we also have, both L and an R. Sorry, both L and the C. Okay. That one deserves some extra calculation. So, for instance, we have, let me see, what did I say? It was Z1 over Z2. Okay, so that becomes Z1 over Z2 is I omega L over 1 over I omega C. Now this is a weird circuit, because this is a circuit that goes like this, and the impedance actually, when the resistor and the capacitor are the same, the total impedance, so Z total, is I omega L minus 1 over I omega C. So at resonance, this thing is 0. Okay. That's not realistic, right? Because any kind of circuit, except when you are using superconducting circuits, but even then, usually you get some dissipation. The total resistance for such a circuit would not be 0. So that brings me to the other point, is that when we do this kind of analysis, we have this very idealized behavior for circuits. And usually when we have, for instance, those of you that are TAs for the 220B lab, when you have an LC circuit, we usually add a resistor to it, just to kind of hide the fact that inductors and capacitors actually have losses as well. Most of the time, those losses are frequency dependent, and the same thing with inductors. So it will have some finite resistance. So this is usually where you hit the limit where circuit elements cannot reasonably be expected. Oops. To be ideal. So most of the time include some kind of a resistor, some kind of an effective resistance that could include effects of the losses in the capacitor or the inductor. So let's talk about losses. So for instance, in an inductor, well, first of all, inductors are made of, let's say, metal or semiconductor, just regular conducting materials. So even if it's just a wire that's wound in a spool and is not even wrapped around some kind of a core with extra, more important magnetic, permeability, so you can get a higher inductance for the same package size. Even if it's wrapped around a vacuum, you still have wires that have some kind of a finite resistance. So usually then what you do is you take an inductor and you'd include a little resistor, and these are your losses. So once you have those quantified, you can say, okay, well, now I have my losses. So capacitors also have conductance losses. But usually, also dielectric losses. And this is something when you select a capacitor, you would find out what those dielectric losses are, and it's usually specified as some kind of a loss angle, and it becomes very much a material science problem. But the long story short is that there's some kind of a table that allows you to figure out, okay, what is the resistance I need to pick for this capacitor. You could also sometimes model it as some kind of a loss here. Okay. Now, parasitic elements. So let's say I have a capacitor and I'm trying to drive a really high frequency circuit current through it. So it goes back and forth. Usually at some frequency, I need to start including that wires have inductance. So usually you need to start adding an inductance in your model, and you could put it on the input or put it on the output, to capture the fact that these wires will have some kind of a parasitic inductance. And it's a function of the fact that these capacitors have a finite size. And they need to be connected in some kind of a circuit, and you're going to need to use some kind of a wire to connect these circuit elements together, and wires have inductance. So you should include an inductance there. Similarly, when you have an inductor and you try to drive a high frequency current through it, there's usually a parasitic coupling. There's usually a parasitic coupling between the windings of the solenoid, because these are metal pieces that are placed super close together. In fact, for high inductance, you want your windings to be packed really tight to get a really high inductance in a small form factor. So what you need to do is you need to consider the fact that at finite frequencies, there's going to be capacitive coupling between the windings. So inductors, a parasitic capacitance between the windings. And usually, when you buy an inductor, it'll tell you what the frequency is that you can still consider this a proper inductor. And you would use it. So you would use it below the frequency called the self-resonant frequency. And the self-resonant frequency is where you have a capacitor and you have an inductor in parallel. At some point, the impedance of the inductance goes up and the impedance of the capacitance comes down. So there's a frequency where they're exactly equal. And this thing is like an open circuit, and it's a resonance. And below that, you can kind of consider it as an inductor, but stay far below that frequency where it's a resonator. And above it, it's basically a capacitor. So you can't use it anymore. So when you start building circuits and filters and you buy your circuit elements, most of the time, when you do things like labs, the 220B labs, a couple of kilohertz and something, you can usually be okay with selecting elements and don't have to worry about the self-resonant frequency. But if you go to higher frequency circuits, that's a thing that you're definitely going to have to pay attention to. All right, now another aspect is we've done this thing where we drive this circuit with some kind of a source, and then we have an ideal meter there. When you go to really high frequencies, that's really not realistic, because usually what you do is if you have some kind of a wire and you have a source, high input impedances cause reflections. So what are we talking about? Well, let's say we have some kind of a circuit. So circuit, put it in a box. And then we take some kind of a cable, could be a BNC cable, could be an SMA cable, doesn't really matter. And then you put this and you connect this, let's say, to an oscilloscope. Now, the problem is at high frequencies, this thing is a waveguide. So you need to consider the fact that it has a built-in capacitance and inductance. So it's with distributed capacitance and inductance. And usually when you design or when you buy a cable, it will have a characteristic impedance. So it's usually 50 ohms. 50 ohm impedance. And what that means is it sees a 50 ohm impedance, but then if the input impedance of the oscilloscope is not 50 ohm, you're going to get reflections. And what does that mean? Well, let's say you have some kind of a square wave that comes in. Not all spectral components of that square wave get absorbed by the oscilloscope. The higher frequency stuff gets reflected. So what you do is you put a 50 ohm resistor in parallel with the oscilloscope input. Or the oscilloscope or the scope may already have a 50 ohm input. Some of them you can select it, such that you get no reflections. And that means that you can cleanly get the signal out of your device. So in that case, obviously, if that's a 50 ohm that is in parallel with your capacitance, you need to design your circuit very, very differently, because that 50 ohm, so let's say you have a resistor now here, that 50 ohm from the point of view of your circuit is going to sit here, 50 ohm. So you should consider the fact that there's going to be a 50 ohm impedance in parallel with the capacitor. And designing circuits for higher frequencies means that you need to start including these kind of considerations. So the long story short, the way we've been doing filters is kind of the intermediate AC frequency circuits. For higher frequency circuits, that's not realistic because you cannot get a clean signal delivered to a high input impedance with a cable, because the cable, once it has a certain length, it's going to cause reflections. All right, input impedance. So the way to read input impedance is, let's say you have some kind of a cable. And then you have, let's say, a B and C port here. It's a coaxial cable. This is your detector. Could be a scope, could be some kind of a other device. So the way to model the input impedance is as just an impedance that goes between the pin, the center pin, and the shield. That's the input impedance. So if it says it's a 50 ohm input impedance, you should assume that this is just a 50 ohm resistor. But it's a 50 ohm resistor that is also a 50 ohm resistor up to the highest frequencies for which it's specified, because it's not just a resistor, it's probably a resistor with all sorts of other funky stuff applied to it. So that's what we mean by an input impedance. So that's the input impedance. And similarly, output impedance sits on the other side. So let's say in this case, we have some kind of a signal that travels through a cable. The output impedance, you can have some kind of a B and C connector. And then you connect your B and C cable. And the output impedance here sits here. So that's the output impedance. Come on. So really, you can consider it input impedance, output impedance, just an impedance that shows up between the two connections that are on that connector that you plug into your instrument. Bandwidth. So let's start with a simple RC circuit. And we're doing this in intermediate AC frequency, so we're still going to use that old-fashioned way of looking at the transfer function. And we know that the transfer function for this thing is 1 plus I omega RC. This one. Oh. All right. Now, we said that this is a low-pass filter because the limit where omega goes to 0 of H is 1, and the limit of omega going to infinity of H is 0, right? So low frequencies get passed and high frequencies get blocked, okay? But this is not really very realistic way of describing limits, right? Because the 0 frequency, what the hell does that mean, right? So it's a frequency that's much, much lower than the characteristic frequency, which determines when this filter goes from a low, from passing to blocking. Okay, so let's be a little bit more accurate. So if you look at the modulus of this thing, so or the length, So, and you plot that. Okay, it's 1 here, and at some point it goes to 0. And usually what we want to say is well, what is the frequency at which this transition occurs? Because that's really the thing we should compare our frequency to. So it's somewhat arbitrary where you draw that line, right? Because it's a smoothly varying function. We could have put it here, we could have put it here, it doesn't really matter. But the convention is you place this point where the modulus is 1/√2. And of course you do that because then, oh, I forgot something. That's -1/2. Because if you do that, then your the argument in that parentheses just becomes 2. So that means you have 1 plus omega squared r squared c squared is 2, which means omega squared r c is 1. Sorry, I wrote this down too fast. These are, no, that's correct. Yeah, so omega is 1/RC. So that's the characteristic frequency at which this filter goes from passing to blocking, right? So here it's passing, pass, and here it's blocking. This is not a very, very sharp filter. You can have filters that are more fancy. They will have like a much, much sharper transition. There's a whole field of study dedicated to it. But what I want you to know now is that when we talk about those limits, really what we're supposed to say, the limit where omega is much, much smaller than 1/RC of h is 1, and the limit where omega much, much larger than 1/RC of h is 0, right? So then we are really comparing things, finite things to finite things, but we're just saying we're in a limit where one is just much larger than the other. It's a little bit more physically realistic. Okay. Now, once we have that characteristic frequency, we now say there's this thing called a bandwidth. And the bandwidth for this filter is 1/RC. That's what we call the bandwidth. And it's just another way of saying, tell me how big the frequency range over which this filter passes, with the understanding that it's not going to be 1 exactly equal up to exactly that point. But roughly speaking, that's the frequency. If you stay below the bandwidth, your frequency comes out. If you go above the bandwidth, the frequency doesn't come out, signal doesn't come out. So that's what we mean by bandwidth. And of course, that characteristic frequency, it translates also for, let's say, instead of the resistor capacitor, let's say, we could build a network like this. It would have a bandwidth of, let me see, it's where omega L is equal to R. So the bandwidth is R/L. That's your bandwidth. This is another one of these filters that has a transfer function that looks just like the one we drew before, except we swapped our capacitor for an inductor and we took the transpose of the circuit, right? Because the resistor was in that horizontal branch first, and now the resistor is on the output port of the circuit. So this is bandwidth R/L. So sometimes this thing is called omega naught, but you will also find this thing being called the 3 dB frequency, because 3 dB is roughly 1/√2. Of course, dB, remember, dB is decibel. It's the log minus the log. All right. So finally, let's talk about the bandwidth of an RLC circuit. So let's take as our RLC circuit, let's take, let's take a resistor here, and let's put the inductor here, the capacitor there. Okay. So your prompt, calculate the bandwidth of this circuit. All right. For those of you furiously scribbling along, hopefully you got there about as fast as I did. Okay, this is not a complicated problem. Just takes paying attention to where your pluses and your minuses go. Let's first get rid of this thing. So the transfer function we get in the same way as we did before. We're always going to get, 1/1 plus the ratio of those two impedances. Now in this case, the impedance number 1 is the resistor. The impedance number 2 is that series combination of the capacitor and inductor. All right, and then to get the magnitude of that transfer function, it's a handy trick to know if you do a lot of these in with complex numbers in Cartesian form, is that the magnitude of a complex number that is of the form 1 over a complex number is the same as 1 over the magnitude of that complex number. So you don't need to do the weird thing with multiplying by the complex conjugate and all that stuff. So you could just take only that thing in the denominator, which is just a straightforward Cartesian complex number. It's a real part, an imaginary part. You square them, you add them, and you take a square root. And of course, there's a minus sign there because it's still 1 over that. The resonance condition is where that argument of 1 over the square root of that thing is 1, and that resonance condition is just 1 over root LC. And then the bandwidth, we're again using for the bandwidth where that transfer function, the magnitude hits 1 over root 2. So really only the solution we're looking for is where that omega L minus 1 over omega C squared is R squared. So you take the square root, but now it's super important here that you pay attention to the fact that minus R could also be a solution. So put the plus minus there. And then bring everything over to the left-hand side, multiply all 3 terms by omega C. You see that I inverted the plus minus, it became a minus plus. It's a good idea to do something like that, even though in the end doesn't really matter too much because both are still valid options, but just to keep track of the fact that that sign inverted. So when you want to backtrack to a particular solution earlier on in your derivation, you'll know that, well, where you have a minus 1, where you have a minus now, that used to be a plus before you moved it over to the other side. And then we use the quadratic formula, and we pick up another 2 possibilities, plus minus. So that omega has 4 possible solutions. So I have a plus minus in red and a plus minus in blue. That term under the square root is bigger than that RC, right? Because it's the square root of R squared C squared. You could factor the RC out, and then you'd have a square root of 1 plus something. And that something is bigger than 0. At least let's hope it is. So that term in the square root is bigger than RC. So when we look at these four solutions, when they're both positive, the red and the blue signs are both positive, that frequency is positive, so we're good. When they're both negative, it's obviously negative. But then if we subtract that square root from the RC, that's going to be a number that's smaller than 0. That's not physically realistic. So we're going to ignore that one. And we keep only the one where we subtract the red from the blue, because the square root is bigger than the other one. And then if we want to know the difference between these two, that term with the square root, it just cancels out because we subtract it out. And we get just 2RC over 2LC. And the bandwidth is simply R over L. So it turns out to be a very, very straightforward, very straightforward expression that really does not depend on the capacitance at all. It's just R over L. But of course, the resonant frequency depends on capacitance. So you have 3 circuit elements, and by choosing your R, your L, and your C, you can choose the resonant condition as well as the bandwidth. There you go. All right.